Okay, let's give another one of these video lectures a try to make up for the time we lost yesterday while I was traveling. I want to bridge the gap between where we were on Monday when we introduced the momentum equation and our applications of the momentum equation to solving practical problems. Updated schedule here, which I'll also recap in the email. Most importantly, the homework will be pushed back to Monday because I know you're going to need a little bit more time. And also, we will have a quiz tomorrow, but that will cover the continuity equation and all of its glory. But for the momentum equation, it will only cover these conceptual aspects. I won't have any problems on there asking you to actually solve momentum problems because we need a little bit more time to practice these. So here we go with our three conservation equations, and we're still focusing on the momentum equation. As soon as we get this wrapped up, moving into next week, we'll start talking about the energy equation. So back to the origin of the momentum equation, keeping in mind that it is simply the application of Newton's second law as applied to a fluid. So similar concepts to what you've seen in physics and calc and other courses in the past, only now we're going to think about how Newton's second law, which is also known as conservation of momentum, can be applied to a fluid. We got there through a very simple derivation where we simply used momentum as the extensive property within the Reynolds transport theorem, which means that the intensive property becomes just the velocity, and we come up with this general form of the momentum equation. And we can look at the various terms a little bit more carefully and recognize that the first term represents how the momentum is changing within our control volume with respect to time. So this is the unsteady component, and it represents a local change in conditions. Really, it's quite similar and analogous to a local acceleration. And the next term represents the change in the momentum between what is coming in and what is flowing out. So we have momentum entering our control volume, we have momentum exiting our control volume, and we're keeping track of how that changes. And those two components will be balanced by the forces that are acting on the control volume. So don't set this equal to 0 over here like we did with our continuity equation. Instead, we're setting this equal to the sum of the forces that are acting on our control volume. So let's work our way through our assumptions again really quickly. We talked about how we can simplify our momentum equation by assuming that the flow is normal to our control surfaces. The consequence is we drop our dot product from our second velocity term over here when we're considering the flow of momentum in and out of our control surface. But we do, as I pointed out in lecture, want to make sure that we maintain the vector associated with the other velocity term, because momentum is a vector. The sum of the forces are vectors. Each of the individual flux terms are vectors. So we want to make sure that we maintain that as a vector, even though this other velocity term now is no longer a vector because it is just representing the magnitude of the velocity as it is integrated over an area. In other words, this is a mass flow rate, and a mass flow rate is a scalar, not a vector. The next assumption we discussed was assuming that we have uniform flow across our two control surfaces. So when we make that assumption, we lose our integration here and turn that into a summation because we're just adding it up for each inlet and each outlet. And this is a good place, I'm just taking a closer look at that form of the equation to point out some of the terms and think about how this all builds upon each other. So the first one I want us to focus on just a little bit is thinking about how over here with our outlet, and same thing with our inlet, we have an area and we're multiplying it by a velocity. And hopefully you see that now and think, wow, that's something we've seen before when we dealt with the continuity equation. That's the volume flow rate, right, that we represented with a Q. So that might have units of meters cubed per second or feet cubed per second. We then take that and multiply it by the density over here, the density of our fluid. Well, that would end up with units of something like kilograms per second or slugs per second, which hopefully now sounds familiar to you because that is our mass flow rate. All right, so in this case, it's the amount of mass that is exiting our system. If we take the density and multiply it by the area, multiply it by the velocity. Well, if this is a mass flow rate and we take a mass flow rate and multiply it by a velocity vector, That gives us a mass times a velocity, which of course is a momentum. So multiply that out and we identify a new term here that we're going to refer to as the momentum flow rate. So add those all up. These two summations represent the amount of momentum that is exiting our control volume, and this other term over here is the amount of momentum that is entering our control volume. And then just a reminder that this unsteady term over here was how the momentum within our control volume is changing with respect to time, all balanced by the sum of the forces that are acting on our control volume. So let's keep going through our assumptions. Next one that we might be able to apply for some situations is that of steady flow. And when we can assume steady flow, we are able to drop that partial with respect to time. So we're no longer worried about how the momentum that is contained within our control volume is changing with respect to time. And that comes down to a form of the control of the momentum equation here that's a little bit easier to wrap our heads around, because we're simply saying that the change in the momentum between what is entering and what is exiting is a function of the amount of force, net forces that we apply to our system. So now we have normal, uniform, and steady flow. Just like with the continuity equation though, we don't necessarily need to add these all up. We could have steady flow that is non-uniform, that is not normal to our control volumes, etc. But this one represents if we have all of those assumptions present. Okay, now for our incompressible assumption, we discussed on Monday that we need to be careful with this one. It doesn't help us out all that much in and of itself, because our tendency is to get rid of the density like we did with the continuity equation. But unlike the continuity equation, where we had this entire relationship and set it equal to 0, with the momentum equation we're setting it equal to the sum of the forces, meaning we also would need to divide those forces by our density, which only makes our life harder. That doesn't really get us anywhere. So when we have an assumption of incompressible flow, all that really does for us is allow us to recognize that rho is going to be the same throughout our system. We don't need to worry about how it's changing from one place to another, but generally it doesn't do us a lot of good. We can't start canceling things out or getting rid of terms or anything like that. So make sure that you keep your density in there as long as you're working with momentum, because otherwise your units aren't going to work out and you're going to get yourself into going down the wrong track. Okay, the last of our new C11 assumptions was our one inlet and one outlet. Let's think about what that does for us. First of all, just reiterating that this term of area times velocity is just equal to our flow rate, right? So we might call this Q out and Q in. You know, if we know the area and the velocity, you can work with those. But if you're given the flow rate alone, you can just recognize that, yeah, that's the discharge, the volume flow rate, Q out and Q in. And you know, to rearrange this in terms of one inlet and one outlet, it would simply look something like this, right? Where we've got the amount of momentum that's exiting our control volume and the amount of momentum that's entering our control volume. And just to break down these terms again for you in a little bit more detail, recognizing that the density multiplied by a flow is equal to the mass flow rate. Okay, so we have a volume flow rate, we have a mass flow rate. A mass flow rate multiplied by a velocity vector gives us a momentum flow rate. So at this form of the equation, it's starting to get pretty nice here. It's starting to get pretty simple, that we see that the sum of the forces is equal to the change in the momentum of what is entering our system compared to what is exiting our system. So we have the mass flux, or excuse me, the momentum flux out versus the momentum flux in. Okay, so this is what our equation looks like when we have normal, uniform, steady flow with one inlet and one outlet. Okay, now this is where it can help us a little bit to go back to that incompressible assumption, because if we set up the equation looking like this, pull over from the last slide and recognize that rho 1 equals rho 2, we already know that Q1 equals Q2 because of the continuity equation. We can lump those, recognize that the mass flow rates have to be equal to each other, and develop a form of the equation that looks like this, okay, where this first term is our mass flow rate, the second is the change in the acceleration. Okay, so again, rho times Q, mass flow rate, mass flow rate multiplied by change in velocity from our inlet and our outlet. Well, that's a convective acceleration, right? V1 representing what the velocity was coming in, V2 what it was going out. Change between V2 and V1 is the acceleration as it moves through our control volume. We've got a mass multiplied by an acceleration. It's actually a mass flow rate, right? We know that that equals the sum of our forces. So Newton's second law. So overall, we can also think of this as our change in our momentum flux. Okay, mass flow rate multiplied by acceleration. The first group of terms is the amount of momentum leaving our system. This other one is the amount of momentum entering our system. So we're saying that the sum of the forces is balanced by the change in the momentum flow rate between the inlet and the outlet. So for the normal, uniform, steady, incompressible, one inlet, one outlet, our new C11 form of the equation, we could simply designate it just like this, delta momentum flux, or momentum flow rate, as we've been describing it in here. Okay, so that's it for the assumptions. Just keep practicing those, get really comfortable with them as they apply to the continuity equation, as they apply to the momentum equation. The application of the assumptions are fairly consistent with a few differences to keep in mind, such as, as I pointed out, that the density is something we need to be careful with when we're dealing with the momentum equation, because of the fact that we need to balance the units properly with the sum of the forces. Okay, so with that, I want to work our way through an example here in quite a bit of detail, and then I'm going to touch upon your homework set. Okay, so we started this really quickly on Monday. I wasn't able to work through it in class, so here's the situation, and this is pretty similar to one of your homework problems as well, but we've got a sluice gate. We've dealt with sluice gates when we were working with the with the Bernoulli equation, and also with the continuity equation, and with energy grade lines and hydraulic grade lines, etc. So it's a very useful representation where these concepts can be applied. So you have a sluice gate with the dimensions as shown, 8 meters deep upstream, 1 meter deep downstream, a velocity coming in at 1 meter per second, not 0, it's coming in at 1 meter per second. And in this case, we're going to have a system that is 3 meters wide throughout. Okay, so constant width of 3 meters. And we want to determine what the anchoring force is, the horizontal component. So there's already going to be an anchoring force that needs to hold this gate up. That's a structural problem. We're trying to figure out what is the force acting on this gate as a result of the fluid, the water that is moving down through the system. So what we're attempting to determine is the anchoring force required to hold that in place. Okay, and this is the order of operations that I would like you to work your way through as you solve these momentum problems. If you work it through with these steps systematically, you will have a lot of success. Okay, this is the way to do it. You can get creative if you like. It'll probably not work as well. So please try to follow these steps where we define our control volume, define our control surfaces, work our way through our assumptions. Based on those assumptions, determine the correct form of the equation that we want to use, put our momentum terms on here. So where do we have momentum entering our system and exiting our system? Put our forces on here. So very similar to a free body diagram, except it's a control volume approach. And then finally, after doing those 6 steps, we can solve it. So don't just jump to step 7 thinking that you are smarter than everybody else in the room. Take this step by step, and you'll get yourself there. All right, so let's take this one on. So shrinking my little steps here so we can keep track of them. First thing that we said we want to do is put a control volume on here. Okay, so sometimes the control volume is fairly obvious. Other times you really have to think it through and try to be clever to save yourself some work. In this case, I'm going to suggest this right here is our control volume, where we're pretty much just capturing the volume of water that was shown there. But hopefully it'll become obvious why I drew it the way that I did as I add on the other terms. Our control surface then is where we have fluid entering and exiting our system. So it's entering to the right and exiting to the left. I'm going to call those CS1 and CS2 for control surface 1 and control surface 2. Okay, so that's our control volume. So we first need to understand what our control volume is and our control surfaces, what they are, before we can think our way through our assumptions. But now that we've got this, we can take it on. So the first thing that I want to recognize here is that I've got flow that is normal to the control surfaces. And I'm able to make that assumption because I've drawn my boundary far enough upstream and my exit far enough downstream that my flow can be fully uniform by the time it approaches those two locations. If I had it right here at the exit, I wouldn't be able to make that assumption because the flow as it's leaving this area is extremely complex. Okay, so I'm able to make this assumption that I've got flow normal to my control volume because of that. And similar rationale behind assuming that it's okay to assume that I've got uniform flow. Okay, if I'm far enough upstream and far enough downstream, I'm really only concerned with what the mean flow, the mean velocity is that's carrying my momentum in and out of my system. Steady, sure, we don't have any information here that it's not. This isn't a reservoir that's slowly draining. This is a system where I've got a consistent velocity coming in, a consistent velocity going out, so we've got steady flow. Incompressible, sure, we've got water, no change in temperature or introduction of a different type of a fluid like an oil or something like that, so yeah. And obviously we have one inlet and one outlet. We've already drawn those. So we're able to go all the way to our Newcy-1 form of the equation. Okay. So the next thing I want to do is indicate where I've got momentum and where I have forces. So I've indicated the momentum. I'm using these green arrows. So where I've got mass coming in, I've got a velocity of 1 meter per second. I've got momentum that is being transported by that velocity. So I've got momentum coming into my control volume here on the left. I've got momentum exiting my control volume down here at the bottom to the right. And let's just chew on that for a little bit. What do you think? Do we have more momentum coming in or more momentum going out? If momentum is our mass flow rate multiplied by our velocity. Well, what's happening with the mass flow rate? Well, according to the continuity equation, we would expect that our mass flow rate at cross-section 1 and cross-section 2 is the same. Right? We're not creating mass, we're not destroying mass. How about the velocities? Well, according to the continuity equation, we would expect the velocity to increase. We've got less depth here, so a smaller area, some more velocity. So we're creating momentum in the situation, okay? Or we're adding momentum to our system, and that must be occurring because of the forces acting on our system. Okay, so what are those forces? Well, first of all, we've got a hydrostatic pressure distribution upstream here, right? Going from 0 at the surface to a maximum at the bottom. We know how to do those calculations. We'll have a chance to refresh here. And again, I've drawn my control volume, my control surface far enough upstream that my streamline curvature is negligible, which allows me to assume that we have a hydrostatic pressure distribution. Downstream, same thing. I've got a hydrostatic pressure distribution, this time acting from right to left. So it's pushing in on my control volume in that direction, and I've put my surface far enough downstream. Streamline curvature will be negligible, and I'm able to assume a hydrostatic pressure distribution at point 2 here. So that's my force due to pressure at point 2. And then I've got my gate that is acting on my control volume. Right? If I took this gate away and needed to represent it through a force, I'd have force due to the gate. And this is another point I want to emphasize is keeping track of the direction of these things. I've put this big X arrow on here to indicate that I'm only solving everything again in the horizontal, which is my X coordinate. And in this situation, I am entirely sure that the force must be acting towards the left. So this time I have made that assumption and drawn my arrow towards the left. And I want us to think about how that influences our final result when we get to it. Sometimes, though, it is not obvious in which direction the force might be acting. Sometimes it's just a little bit too complex. Sometimes you don't even know because it depends on the flow conditions. So if I'm not positive which direction the force is going to be acting, I always will draw my arrow facing the right. Because when I do that, if I get a positive number, I know that yes, indeed, the force is acting towards the right. if I get a negative number, I know that my force was actually acting to the left, and that's why I got a negative number. Okay, I'm going to try to make that point a little clearer as we talk our way through these, but keeping track of the directions is really important. Again, we're dealing with vectors here. Okay, so even though we're only solving this in one direction, we still have to keep track of, well, in which direction are these different things happening. Okay, so those are our forces. So let's take this on. Okay, we're up to step 7. Let's try to solve this. Okay, so first thing, hydrostatic, well, let's rearrange our equation a little bit. We're trying to solve for the force acting on the gate. Really, I should have left little vector hats on each of these over bars, but because I'm only solving everything in x direction, really what's important is that I'm keeping track of the signs. But really, it'd be best to put, I could just do that quick. We should have little vectors on each of these, little over bars. The velocities too, right? Okay, so what I was getting at though was to rearrange our equation to solve for the gate. And oh good, I put my bars on there correctly this time. So there's the relationship that I need to solve. So we need the forces due to our hydrostatic pressure at point 1, or cross-section 1, cross-section 2, and then change in the momentum flux, or momentum flow rate between our outlet and our inlet. FP1, we've done this before, right? So back to chapter 2. It's just going to be gamma times the depth to the centroid, which in this case is going to be the depth of the water divided by 2, multiplied the cross-sectional area. And I went through these numbers pretty quick this morning, but I think these numbers are right. Okay, so I've got 9.408 times 10 to the 5th newtons. That's my total force on this control surface. Do the same thing over on the other side. Okay, so this is my total force due to hydrostatic pressure at point 2, acting back towards the left, 1.47 times 10 to the 4th, if I'm not mistaken. Okay, and then from continuity equation, I can calculate my volume flow rate, Q. No problem if I did that right. Okay, so I think I have 24 cubic meters per second that are moving through this system. With that, I can also calculate what my velocity is at point 2. I can also just see it intuitively. If I go from 1 meter per second at 8 feet deep, and then I go to 1 meter deep over here, I've got to have a velocity of 8 meters per second below my sluice gate. Okay, so now I believe I have all the terms that I need. As I indicated earlier, these relationships, right, this combination right here is our change in our momentum flow rate, delta mo. So this delta mo dot is equal to this term, which is 1,000 kilograms per meter cubed, which is my density, times my flow rate, times the change in my velocity. And for that term, I came up with 1.68 times 10 to the 5th newtons. So I've got all my terms. I can just plug them all in, all right? Just cleaning it up right here. And this is what I came up with. So 7.581 times 10 to the 5th newtons. Okay, so that's our raw number. I can take that and turn this into something that's a little bit more reasonable, watching our sig figs. So if I convert that to kilonewtons, I find that the force on my gate is equal to 760 kilonewtons. Okay. All right, so that's the main example that I wanted to work through. And I want to just think through some of the applications based on your homework. Oh, almost forgot to point this out again. That we always want to, because it is a vector, make sure that we are really clear about the direction that our force is acting, right? And as I pointed out at the beginning, I made an assumption, and I was very confident because of this particular configuration, it's quite obvious that the force must be acting from the right to the left, right? It's directed to the left. So we always want to be clear and indicate that in our answer as well, okay? So I've got a force that my gate is applying to my control surface at 760 kilonewtons, okay? Directed towards the left. All right, so I want to just spend a little bit of time setting up your homework set, okay? And let's just think about how these different things apply. I'm going to spend a little bit of time on this nozzle problem because it's another really great way to think about how these concepts apply. With the others, I'm going to not take it near as far because they're your homework set and I want you to solve them, but I do want to make sure that you're headed in the right direction. Okay, so let's think about it. We've got flow that is from left to right. It's going through this nozzle. The purpose of a nozzle is to accelerate the flow, so we have a high-speed jet coming out on the other side. This one looks like it's pretty successful because we're going from 25 feet per second to 100 feet per second. And this goes back to some of our lessons from chapters 2 and 3, where we have a pressurized system here inside of our nozzle where the pressure of 0.1 is equal to 75 psi. But we know that if we have a free jet, which that's what this nozzle is generating, is a free jet, that the pressure outside of our nozzle is equal to 0. And maybe see where this is going, okay, as we start working our way through the system. All right, but let's go through our steps. So first up, we want to draw our control volume. Okay, pretty easy here because it was more or less indicated for us already. Now we want to indicate our control surfaces. So I've got one at the upstream where I've got flow entering my control volume, one at the outstream where it's exiting my control volume. Call that CS1 and CS2. Okay, now that we've defined our control volume carefully, we can work our way through our assumptions. And this is pretty similar to the last one, right? We've got flow that is normal, uniform, steady, incompressible, and one inlet and one outlet. Okay, think your way through those, but I think they're all reasonable. We can talk more about that in lecture on Friday if you need clarification. Okay, so with that, we know that we can go to our new C11 form of the equation. Everything's happening in one direction, so we're just going to sum this all up in the x direction, so we only have to worry about one coordinate direction for this problem. Okay, so with that, we can next indicate where we've got momentum moving in or out of our control volume. So we've got momentum entering on the left side, we've got momentum exiting on the right side, so we're going to represent those with μ.1 and μ.2. Okay, and then let's think about what forces we have acting on the system. All right, so like before, we have a force acting on the right side of the equation. Okay, it's a hydrostatic, or sorry, it's a static pressure, okay, and it's equal to 75 psi. And I got ahead of myself there, but I wanted to point out it's a common mistake here that some people will tend to draw a hydrostatic pressure distribution in this situation. But that's not the pressure that we're concerned with. This is a pressurized system. There's a pump or something upstream, or maybe it's in a water tower or something like that, that is driving it with a 75 psi. And when we see a term like that represented, that's indicating that that's the average pressure that's acting across this entire control surface. So in reality, it's going to be a little bit less than 75 psi at the top, a little bit more than 75 psi at the bottom, because there is a slight variation due to hydrostatic pressure, but this is over 3 inches when I've got a background pressure of 75 psi. So we're not worrying about that. We've got an average pressure of 75 psi. Okay, how about at the outlet? Well, it's a free jet, right? So our pressure at the outlet is equal to atmospheric conditions. This is a gauge pressure, 75 psi. This P2 of equal to 0 is a gauge pressure. So as long as we're consistent, we can solve this all in terms of gauge pressures, in which case we don't have a pressure distribution at the outlet because it's a free jet. Okay, so there is no pressure at point 2, and therefore we don't have a force due to pressure at point 2. So we only have a pressure force on the inlet of this particular control volume. Okay, hopefully that makes sense. Anything else? Do we need to worry about any other forces acting on this system? We would have a weight acting on it, but that's going to be in the y direction, and we're trying to solve things here in the axial direction as specified in the problem, so in the x direction in this case. So we're not worrying about that one, but we haven't accounted for the fact that we've got this nozzle, right? So we've got some force due to the nozzle acting on our control volume. The direction here is probably a little bit obvious, a little bit intuitive, but this is an example where it's not always clear which direction that force might be acting. So as I suggested on the last problem, if you're not entirely clear which way it's acting, draw it to the right and then see how it comes out. If we solve this problem the whole way through and we end up with a positive force nozzle, we know that yes, indeed, it's acting to the right. If we solve it through and we end up with a negative force, then it must be acting to the left. Okay, so just let the math take care of itself if it's not obvious which way it's going. All right, I'm going to take this one just a little bit further, but I'm going to let you work through this a lot on your own, okay? So let's take it a step further. We're going to be able to use our new C11 form of the equation, which looks like this. And what do you, so if I plug in our forces that we identified, it's going to look something like this form of the equation. I lost another one of my overbars. I really should be more careful with those. Okay, so I should have an overbar here. Those are both vectors. And I can solve that for the force of my nozzle. So it's saying that the change in my momentum minus the force at pressure 1 is what the force of my nozzle is going to be. Okay, but what's our force pressure at 1 going to be? Okay, as I pointed out, it's not the hydrostatic pressure distribution that we're worried about here. It's this background gauge pressure that was specified. How do we get that to a force when we're given a pressure? Hopefully that one's obvious. If not, go back to chapter 2 and reevaluate a lot of things. And again, pay attention to the sign. Okay. Other than that, I think you're ready to roll. Everything else has been specified. You need to figure out what your flow rate is. You should be able to do that by now. You should be able to get this force pressure term. You're going to be able to solve for the force on your nozzle. If it comes out to be positive, well, we drew our arrow to the right. You need to indicate that the nozzle force is directed to the right. If it comes out to be negative, it's acting to the left. Okay, this one looks a little bit nasty. A little bit more complicated geometry. We've got multiple things going on in multiple directions here. That's okay. We're going to still go through the same steps. I'm going to leave you to do most of this on your own. Okay, but let's just talk it through a little bit. So first of all, our control volume. Well, we pretty clearly have two control surfaces here. So your control volume, what I would do is probably just draw it as the inside of the pipe, right? With a control surface, an entrance at section 1 and an exit at section 2. Assumptions-wise, think it through, go through the new C11, see what you think is appropriate. It would appear to me that all of our new C11 approximations are going to be reasonable. But where you really need to be careful this time around is you start applying the relationships to this equation is in your directions. Okay, your V1 and your V2 now are not oriented in the same direction. Okay, and those are vectors, right? Remembering that those are vectors, so keeping track of your signs really carefully. Okay, and I want to leave you to think about those a little bit. But we do have a momentum entering our system on the lower part of the pipe. We have momentum exiting our system up above. We do have a force due to pressure here. And this one is also making you think a little bit about your pressures because within the problem, you're first given a gauge pressure for pressure at cross-section 1, and then an atmospheric pressure for that at section 2. And that's a little bit of a trick question, so I'm reminding you of that. Okay, so your pressures are specified in with two different reference systems. Well, you need to get them into the same reference system. It's the bottom line. And it doesn't matter which one you use. You can solve these with in terms of absolute pressure. You can solve these in terms of gauge pressure, but you can't solve them with a combination of those two systems. Okay, so put it into one or put it into the other. One of them is easier. I'll let you think about which one's going to be easier, and then go to it. Okay, I think you can get there. All right, this is a neat one. I'll show a video in class that represents a system that looks like just like this one. Okay, this is a very practical problem, and let's think it through a little bit. I've already popped on the control volume and the control surfaces. I do think it's a little bit tricky. It's not quite as cut and dry, but what I've done is say, oh, well, I need to capture where I've got flow coming into my system. I need it to be where it's going out of the system. I want to keep my life easy, so I'm going to draw these things normal to the control surfaces in both situations, and then I can't just have part of a control volume over here on the inlet and part of a control volume over here at the outlet. I need to be able to capture the whole system, so I've just captured the entire boat. Okay. With that, I've got, so that's my control volume, that's my control surfaces. I can go through my assumptions. I think yet again we're able to get away with new C11. So, but think about that. Make sure that you can justify those assumptions. We've got a momentum flux coming in and we've got a momentum flux going out. But pay attention again to your vectors and the orientation in terms of the different components of those vectors, because you have some stuff acting here in the vertical direction and some stuff in the horizontal direction. The outlet's acting in both directions, so you're going to have to solve two different equations here. You're going to have to think about what's happening in the x direction and what's happening in the y direction. Or at least, I should take that back. You don't actually have to solve two equations, but you should realize that you need to break it up into those two components. But the problem, if I'm not mistaken, specifically was asking you about what's happening in the horizontal direction. So that's the only one that you're actually going to have to solve. So I've once again reminded us of the x coordinate here. Okay, so go to it, give that a try. This is a fun one. Okay, so we've got a nozzle spraying straight up, and it's got this plate that's magically staying perfectly on top. We know the mass of this plate. Same thing. We're going to go about it with the same approach. We're going to draw the control volume. You should note this is really similar to your lab exercise, right? So we've got this shooting straight up. I would draw the control volume to capture the water here all the way around. We've got a control surface where it's entering down as it exits the nozzle. We've got it's going out horizontally across the edges here. And I believe you're going to have to solve, you're going to want to apply, again, just one component of the momentum equation, and that is in the y direction. That's how I'm specifying the vertical direction here. Keep track, think it through. How are your pressures changing? How are your momentum flux changing? And how can you break those up into what's happening in the x direction and in the y direction? What forces are acting on this entire control volume? And hopefully I don't have the problem written out right in front of me, but I believe you were told that you can neglect the weight of the water itself. There would be some weight acting on this, but it's a narrow jet over a pretty small area, so the idea is that that force is going to be really small compared to the other forces acting on the system. And the big one that we're worried about is, well, we've got this big plate sitting on top of it. Okay, so pretty interesting problem. And then I think this is the last one we need to discuss together, because the very final problem is the sluice gate problem with different units and dimensions, but otherwise it's the same as the example that we just worked out. And I'm going to give you a little bit of a hint on this one, because it is a bit tricky. It depends on if you notice a few tricks in terms of setting it up, but I'm going to let you know that the velocity at the outlet is equal to 7.07 feet per second. That will save you from needing to solve multiple simultaneous equations, which hopefully you're all comfortable with doing, but it gets pretty complicated, and there's a lot of trigonometry in this one as well. So I want you to be focusing on the momentum equation, not on memorizing your old trigonometric functions. All right, so velocity coming in, two different locations, and they're interacting with each other and creating a new jet that's going off to an angle right here. Okay, and basically we're going to take the same approach. The control volume is going to outline this thing. You have a control surface at three control surfaces, the bottom, the two inlets and the outlet. Assumptions I think are going to be pretty similar, except we obviously do not have one inflow and one outflow. So we're going to have to step back, and we do have a form of the equation for that. Pay attention to it. We got momentum fluxes at each of the control surfaces, and think your way through the forces. Okay, what forces do you think we actually need to consider? Okay, so that's your homework set. So with that, I'm going to cut things off here, give those a shot. We'll have a chance tomorrow to talk about this in lecture in a little bit more detail after the quiz. But I did want to lay a little bit more groundwork here and get you comfortable so you can work towards these solutions. Okay, take care.